Hello, everybody. Welcome to this session. I never thought there are so many people come to this session because I found this room is not easy to find. Okay, I will talk about the new features in Spark 2.3, especially in the advanced analytics and machine learning and deep learning. My name is Ian Bo, and I'm currently a staff software engineer at Hortonworks. And meanwhile, I serve as the Spark PMC member and committer. I contribute a lot of other libraries or frameworks, such as the TensorFlow and Apache MSNet. So most of the time, I work intercept of the system and algorithm for machine learning and deep learning. OK, give you a quick agenda. The first part is what's new in Spark 2.3. And second, how to use the new Pandas UDF, which is very good performance compared with the one row at a time Python UDFs. And then we talk about how to use Spark to do deep learning. The first thing is in Spark 2.3, we add an image representation and readers for Spark dataFrame. You can use it to load data in a distributed fashion. And then we can use Spark deep learning pipeline to train some deep learning models. At last, because the deep learning models usually will involve a lot of dependencies, such as we need to depend on TensorFlow and maybe low-level libraries like NumPython or SciPython and the CUDA or GPU driver. So it's better to for the data scientists to set up their environment to deploy the environment very, very fast. So we can show some examples and demos to running Spark in Docker on Yarn. This is part of the highlight features in this talk. And then for the Spark MLlib, we support hyperparameter tuning. But before 2.3, the hyperparameter tuning can only do in serialized mode. In 2.3, we make it can parallel. And at last, if we don't have enough time, we will give you some slides to show the other new features in Spark 2.3. OK. I think most of the work is contributed by the Spark community members, not myself. So this is the collaborative work of the whole communities. In Spark 2.3, we have a lot of great features, such as for the structure streaming, we support continuous processing, which is a new streaming mode. And we support Kubernetes as the backend. And for Spark Circle, we have a new data source v2 APIs. Meanwhile, we have a lot of Python Spark and ML enhancement. And this maybe we will talk about in the following talks. Let's start with the first highlight features is the Python Pandas UDFs. Spark has supported UDFs since 0.7. Why users would like to use Python is there is a lot of things which is much more easier to express by Python. And Python has a lot of libraries we can use. But the original Python UDF, we use it it's one row at a time, which means we will transform the data from the Spark JVM one row to the Python daemon, and then we process it for one row at a time. So this has a lot of performance issue. The big downside of this, there is a lot of packing or unpacking of rows, and the serialization and deserialization is usually a big impact for the performance. So in Spark 2.3, we have supported the Pandas UDFs. This is a new UDF. We use Apache Arrow to transform data between the Spark JVM and Pandas, which makes the Pandas UDF can run very, very fast compared with the original UDF. We will show the performance later. What is Apache Arrow? Apache Arrow is a in-memory column data format that can use in Spark to efficiently transfer data between JVM and Pandas. And we can say Apache Arrow is just like the in-memory Parquet, because Parquet is column data in the external data storage. So for the Pandas UDF, we support two kinds of UDFs. The first one is a scalar, and the second is a group map. If you want to use this feature, you need to enable this configuration, the spark.circle.exception already enable. Okay, let's show some examples to show how to use Pandas UDF. Okay, the first example is we want to calculate the cumulative probability for a column value, which is the CDF. And on the left hand is the, the left hand is the original UDF, which we'll call the states.norm.cdf on each row, and it will process one row at a time. And on the right side, the Pandas UDF will take the pandas.series as the input and return the pandas.series of the same length. So internally, Spark will execute a Pandas UDF by split the whole columns into batches and operate on the whole batch, and then concrete them together. So in one word, is for the left hand, we will process each row one time, and on the right side, we can process each on the whole batch. And another kind of Pandas UDF is group by map Pandas UDF. Will usually work with the Spark dataFrame group by operation. So it's more like a split, apply, and combine fashion. And first, we will split the data into groups according to the group column. For example, in my example, is the ID columns. And then at each column, at each group, it will be stored at a Pandas data frame. And we will apply the Pandas function in a batch fashion, which is very, very fast. And at last, we will combine the result from all of the groups, and we'll combine them into a new Spark data frame. Okay. Oh, this is the matrix feature of the Pandas UDF. We will not talk it in detail. You can use it. You can refer it after the talk. Let's say the performance. Performance is very good. This is the end-to-end runtime performance comparing the default version Python UDF, and which is the row-based, and the arrow-based, which is vectorized executed UDF. As we can see, we can achieve almost 4 to 200 times speed up across different data sets and different functions. So this result is quite promising. So after the Pandas UDF, we will support another kind of UDAF, which can also power the Spark with Pandas. We want to support a Python version UDAF, which means we will execute the code at Pandas on each Spark executors, and from the perspective, the Spark only used for the scheduling of the distributed job, and at each executor, the job will be run on Pandas. So this is the plan for maybe the coming Spark version. So after if this feature becoming available, a lot of the Pandas libraries you developed before, you can reuse it. So this is the first highlight feature for us. And the second one may be the hottest topics in the past years, the deep learning. And everyone and every libraries, every system want to get some attention from deep learning. So we also saw some great success in deep learning, like the Google Translation, like AlphaGo. And we found that the key algorithm breakthrough happened in maybe 1980s or 1990s, but it became feasible in the past years. I think the most important reason is we can collect a lot of data, and we can use very advanced hardware like GPU. So let's say a typical deep learning workflow. So it will take an image as the input and output a label that described what's in it. In the original machine learning methods, we will use some hand-designed features, and then to put these features into softmax or other classification models. So for the deep learning pipeline or workflow, we may not to do some hand-designed feature learning. We can learn the feature automatically by designing some convolution layer, some activation layer, pooling layer. This may be easy to express using some deep learning libraries like TensorFlow or PyTorch or MSNet. So we can split the whole process, the deep learning process, in two parts. The first part is the feature learning. That's what we talk about, which can include some convolution layer, ReLU layer, or pooling layer. And the second part is, after we get the result from the feature learning, we can put the features into still the same as the machine learning methods, still the softmax or other classification models, and we train the model. So we can say usually the deep learning models is very, very deep layers. For example, 180 layers for some famous deep learning models. So it's very, very complicated for all of us to design deep learning models. So maybe most of us would not do that. And another issue is we don't have enough data. Because we can say, example, researchers from Stanford University developed their neural network models to classify skin cancer. So they use some photograph. Users can use their cell phones to take the picture for their skin, and they can use a trained model to classify whether it's a positive or a negative label, means a EO case or no EO case. So we can compare the two deep learning architecture. The upper is the famous Inception V3 model, and the lower is the Stanford skin cancer model. So we can say almost the architecture are the same. So we can also compare with the training data and the classifiers. Because for the Inception V3 model, we trained it from ImageNet, which has almost 14 million images and 20,000 classes. But for the skin cancer case, which is already very large dataset in the medical research, but still far less than the ImageNet. So I think this kind of case may be more popular or more suitable for the deep learning ordinary use case in across the companies or industries. So maybe transfer learning, you can refer the transfer learning is the solution for this kinds of case. So what is transfer learning? Transfer learning we use some pre-trained model to do feature learning, and then we get some feature representation. We fit them to a softmax or other classification models, and only the parameters of the classification model is we want to learn. For the feature learning part, the parameters is pre-trained. We don't need to update them. So the first part is more like a transformer in the Spark semantics. So, and the second part is like a traditional machine learning workload that we can express it using Spark MLlib pipeline. So let's show how it can be done in Spark framework. Spark deep learning pipeline. Databricks has released open source libraries, which we can use it to do some deep learning works. For example, the transfer learning is one of the case. And then what's the benefit of the Spark deep learning pipeline? We can use Spark to scale out the computation, and it represents a deep learning workflow in an ML pipeline. So we can benefit from the distributed computation ability of the Spark, and we can benefit a lot of features from the Spark MLlib machine learning pipeline. So a great feature is in Spark 2.3, because if we want to run these kinds of features, we need to first load the data in a data frame. And dataFrame is a distributed data representation. And for the most common case is the image data is the case. So in Spark 2.3, we added an image representation and the reader to read the image directly into the data frame. So you can easily load data, image data, and running a deep learning pipeline on them in a distributed way. So we will show a demo. Let's show a demo. Our demo is a transfer learning case. So we use Scala. You can also use Python. Let's show the case. First one is we use the cargo dogs and cats data. And we have 200 images at HDFS. And after that, we will load, we use the read image data API to load the image into data frames. And we can say the schema of the image. Oh, sorry. Okay, I think this we can't zoom out it. Yeah. Oh, I will share the demo, the demos and the tutorials at the GitHub link, so you can download it after the summit. So let's say the schemas. The first one is arrange is the path of the images, and height and width are the height and width of the image, and number of channels, which usually is RGB3 channels, and the format is a string format, and at last is a binary data. We can say show a data frame of the Spark image data frame. It's important because the arrange is the path of the image, so we can use it to add the label for the image, whether it's a cat or a dog. You can say the binary. And the next step is just we say we need to give a label of the image data. So in your case, maybe you have already has the label. I just tag the label according to the path, the file path of the image. You can say if it's a dog, its label is 1, and a cat is 1, and dog is 0. So after that, we have the training data. We want to check, we want to split the training and test data set. You can use it in Spark ML. We can use random split with 80% and 20%. So after we get the training data set, you can say we have about 157 training data sets, and the left is a test data set. And we want to check whether the label is in balance, because if the label is balanced, we can't get a good model. So we will run a circle query to the data frame. We can get the label is not in balance. So we can construct our transfer learning pipelines. Here, maybe it's not so clear. There is a pipeline for the Spark MLlib pipeline. There are 2 stages. The first stage is, we call it deep image vectorizer. It's what it used for. It used for extract the image data using Inception V3 model. It's just like what I illustrated in the previous slides is the first feature learning part, but we didn't train any parameters. Means the parameters is directly come from the Inception V3 models. And after the transformer of this deep image vectorizer, we'll get the feature representation of each image. And after that, we will use a logistic regression. You can say the logistic regression is the Spark MLlib logistic regression model. So the two combine the two stages, we can have a Spark machine learning pipeline to train an image classification model. This is a transfer learning model. Maybe take several times. I will move faster. OK, you can say why I will show these numbers. So if you're familiar with the inception V3 models, you can say the last layer, the parameter size is equals with this. So you can check it. OK, and we can print out the coefficients and the intercept of the logic regression model. Because the feature extractor we didn't learn any parameters. We only train for the logic regression. You can say this is the inception and the coefficients. After that, we have the model. We will do model evaluation to say whether we get a good model or not good model. We can say the accuracy or other metrics. So we still use the multi-class evaluation in the Spark ML pipeline to evaluate the model. We use the accuracy as the metric. And the metric is maybe 95%. It sounds a good model. And after that, if we have new data, we can also do some model predictions, which means we can put the model into production. You can say we can get the prediction result of the model. And some of the results, maybe we can move fast. Oh, it's finished. And some of the models, maybe we can say this is a label and it's a prediction. Some of the instances we predict correct, and maybe others we predict error. So this is a deep learning pipeline. And we can also use Python version to do the transfer learning. OK. Oh. OK. You can get the video and the tutorial in this link, but I didn't put it in, didn't upload it because I don't have enough time. Maybe in 1 week I will upload it. OK, let's summarize some of the work we can do using the Spark deep learning pipeline, just like the demo I'll do. The Spark learning pipeline is very, very powerful, and maybe you can even plug in your own algorithms. For example, you can apply deep learning models at scale with these kinds of transformers. You can also do some image transformer. For example, your raw input data, image data, is not very, very formatted, which means the width and the height is different. So in the deep learning, usually we'll do something in a batch fashion. So you need to make them formatted. I will show a demo how to do it. Usually the operations will happen at Python code or TensorFlow code. So we can use FF image transformer to define a TensorFlow graph to transform the data from one kind of format to another kind of format. And for the transfer learning, and also we can deploy some models in Spark Circle functions. OK. So currently, we can do some work for deep learning. Another issue is just I have talked in the agenda. The deep learning dependency is very, very complex. For example, you can say, what kinds of libraries you need to install to reproduce my demos? At least you need to install these kinds of libraries. So if you want to reproduce my demos, the first thing you ask some system administrator of your cluster to help you install these kinds of libraries. Or maybe there are different version conflict, a lot of pain point. So is there any way we can do it in a very, very unified and very, very quick, fast fashion? So in Spark, in the new Hadoop 3, we supported running Docker on yarn, which means you can define a Docker image and submit a job, and specify the job can running in the Dockers. Then you don't need to configure any environment for your jobs. But can we move the Spark jobs also to running in Docker on Yarn? So we can say one way is we can put them into a Docker image, and the Docker image will help us to set up the environment. So you can say the Docker image. This is a very simple example. We have. I also want to share this in the GitHub. So if you want to find something like this, you can refer the GitHub. Docker image is very simple. We use the base images. This is one of the images in our internal images. And then we install some libraries, just what we need. And after we have the images, we can build the Docker file and then deploy the Docker. How make it to running Spark in the Docker we just built? So we need to pay to configure 8 parameters. But there are 2 groups. One is for the application master of the Spark job, and another is for the executor. So you can say the first is which kinds of runtime you want to use, a Docker or a non-Docker. And then this is the most important. This is just the Docker image we just built with this file. And these are usually you don't need to change it because this is the map from the host password and to your Docker image password. So it will have some authorized issues if you didn't configure it properly. For a starter case, you just use to change this for your own Docker. Okay, let's show a case, show a demo. The demo maybe is, let's check the demo. We still use the Zeppelin as a front end to show the demo. We have HTTP clusters, and there are 5 hosts. And then we have installed Yarn, Hadoop, and Spark with Livy and Zeppelin. And these are not so important. We don't need to use Livy and Zeppelin, but I just want to show the examples very easy for you to reproduce. So we have opened the notebook of the feature transformer. We can say in these examples, we need to configure the session, which is we use Livy to submit the job, so we need to configure the Livy session. There are several configurations. The first is because we want to use the Spark deep learning pipeline, we need to add this as a dependency packages and some of the Python dependency. Because the Spark deep learning pipeline zips some Python files in the jar file, so we need it. And the other 8 parameters is for the configuration of Docker. After we finish these kinds of configurations, we can use this Livy session to submit Spark jobs, and all the jobs will be running inside the Docker image. You can say, first we will show there are 60 images, cats and dogs. But less data compared with the previous example. And then we can show the data, the image, but this image is not a different format compared with the previous one, because I showed this example in the deep learning pipeline, not the Spark 2.3. And then we can show the image. The schema is a little different, so you don't need to worry about it, because the file path is a separate columns. You can still use the Spark 2.3 to load the images. And let's say the feature transformer. We define a TensorFlow graph. What's the purpose of the TensorFlow graph? It will transform an image of arbitrary format, which means the height and width is not unified, into an image with height and height are not, both of them are 299. And then we can feed them into some batch deep learning pipelines. So you can say This is the original image, and this is the transformed image. And what the pipeline do is just make a transformer, and users define the transformer via the TensorFlow graph, or maybe others like Keras models. So it's very easy to reproduce the model. You need to ask your system administrator to install the dependency packages. Oh. Okay, so this is the image. Okay, and the last feature is we want to highlight is we have hyperparameter tuning framework in the Spark deep learning pipelines, but there are some issues before 2003. So the example, we create an ML pipeline include 2 stages. The first one is the PCA, and second is linear regression. So it will make 4 times 4 is 16 parameter grid to choose the best K for PCA and the best regularization parameter for linear regression, which means we will train 16 models and find the best models. Previous Spark 2003, the 16 models, means 16 Spark jobs will submit in a serial mode, which means we will first submit the job, and after it's finished, we will submit another one. So this is not very, very efficient. You can say the Spark job, each time you only have 1 job being executed. It may contain several tasks. So in Spark 2003, we have added parameters to control how many jobs you want to submit in parallel. You can see the result of these parameters. There, we set the parameters with 3. So there are 3 jobs to be submitted in parallel. You can set more larger, but it depends on whether you have enough resource. Okay, so this should be another a great improvement for the Spark ML pipelines. And you can use the pipeline, you can plug in all kinds of algorithms, such as the most popular SGBoost. If you want to know the SGBoost running in Spark pipeline, you can come to the afternoon session. I have another talk about running Spark and running SGBoost on Spark. So there are some other features, several other features. I will give only very, very brief introductions because we have not enough time. One feature is the ML pipeline running on structured streaming, because in the traditional way, before 2003, we only support running ML in the batch Spark Circle dataFrames. But the Spark Circle dataFrames and structured streaming has almost the same API. We want to know we can deploy MLlib models on the structured streaming. So in 2003, we have supported details. You can refer some documents. And another is there are 2 great improvements for the structured streaming. One is the continuous processing. It can support such kinds of millisecond scale latency, because usually the Spark streaming is maybe second scale latency. It can support some millisecond scale, but with limitations supported, only like the map-like operations, like select where map flag. Because in the continuous processing mode, we will launch a set of long-running tasks that continually read, process, and write the data. Since events are processed and written to sync as soon as they available the source, so the end-to-end latency will be millisecond. And stream-to-stream join. Before 2003, we only supported stream join with static table, and we support such kinds of streaming join with stream, but also with limitation. And the ORSA improvement, you can get the details of the ORSA in the afternoon's talk by my college, Dongjing, because the ORC currently can get a 2 to 11 times performance gain in the TPS benchmark, and it's also supported vectorized execution. And the last is running Spark on Kubernetes. So there's a lot of great features, and we don't need time to cover all of them. So that's my talk. Do you have any questions? Oh. Is there any microphones? Oh, I think I can hear you, but I'm not sure all the audience can hear.
Well, thanks for the great talk. Regarding the transfer learning, you said there are two parts. One is the feature engineering part, one is the classification part.
Yeah.
And if you stick to transfer learning for deep learning, so those two workloads will be based on GPUs.
Yeah.
But since you interchange the last part with the logistic regression model,
Yeah.
it could be also a CPU workload, right?
Yeah.
So how do you optimize your configuration for the Docker containers when to use CPU and GPU? Or is it even possible?
Oh, it's a good question. I think it will involve a lot of discussions we have done in our office. First, the feature extraction is more of GPU workload, and the transform learning, the softmax, we will use Spark ML pipelines. It may be more depends on the CPUs. But I think it's not a big issue because currently in the new Yarn features, they support to scheduling GPU and CPU. And in the near future, maybe for Spark job, we will have a configuration to, for example, we ask several GPUs for my job, and maybe like we specify the executor numbers, the executor costs. So this should be, I think, not a good, not a very big issues. We can make it, but we can put the work, push the work to Yarn. And for the Docker issue, I think we can make a configuration for both of them, and it can work well. This is the most simple way. Because the Docker, usually a Docker image, for example, I show my Docker image has only about 200 megabit size, so it's not so large. So usually it's very fast to attach the Docker image to your Yarn job. So I think both we can wrap both the CPU and GPU drivers dependence in the same Docker image. And you can also choose different ones, but I think this is maybe currently is a feature under development. Okay, and okay.
Thank you so much for your talk. At the end, you highlighted some advantages of ORC over Parquet.
Yeah.
In general, you suggest machine learning related tasks better on or to perform better on ORC.
Oh.
It's just in specific cases.
I just, okay, I need to claim it because I may be mislead some of the audience. I say because maybe before the 2003, the ORC performance in Spark is maybe not so good compared with Parquet. But after 2003, I think the performance is very good. It's even better than the Parquet. So either way you can use it. The Spark currently default uses Parquet. If you want to use ORC, it's also okay. And what's the benefit of ORC is if you have Hive clusters, the Hive default format is ORC. So you can interoperate the data with Hive and Spark. So this is a benefit. Okay. Okay. Okay.
One other question regarding the deep learning pipeline.
Yeah.
In the second demo, you showed that you did some image pre-processing, like
Yeah.
there could be any other pre-processing operations.
Yeah.
So the first question is how it's stored internally, the image, and second, is it possible to spill intermediate results, like pre-process the results, to this, so you don't have to do the pre-processing every time you run the pipeline?
Yeah.
Switch to preload or pre-process at runtime?
Yeah. Two questions. I supposed to ask the second question because I forgot the first one. The second is the feature transformer. We can do it and save the data to dataFrame and to the external disk. And next time we want to retrain the model, we don't need to duplicate the transformer stage. So this can be done. Yeah. And what about the first question is we can define any kinds of transformations with TensorFlow graph. It means any kinds of operations TensorFlow support in the deep learning pipeline we will support, because the deep transformer will call the TensorFlow graph. So how the semantics you want to specify is how you write your TensorFlow code. Okay. Any other questions? If no, okay. Thank you.